Okay, so welcome to this first video in the playlist on group theory. Okay, in this video what we want to do is cover the definition of a group. So I want to show you what a group actually is. Okay, so firstly what I want to do is motivate this definition. I want to tell you what we're trying to actually do here by creating these things. Okay, right. So group theory is the foundations of abstract algebra. Okay, and abstract algebra is all about creating new number systems. Okay, so classical algebra is the type of algebra you learn in school. Okay, you learn how to use number systems such as the integers, the rationals, the real numbers, and the complex numbers. Okay, all of that is classical algebra. Those four number systems, they are classical algebra. Okay, abstract algebra is all about asking, well, can we create other number systems with different properties? Those number systems of classical algebra, the integers, the rationals, the reals, and the complex numbers, they are incredibly powerful because they have structures which parallel things in the real world. Okay, and that's why they have incredible uses and why they're so heavily studied. Okay. Now, they also have incredible algebraic properties. We can solve equations in them, okay? Abstract algebra is about creating number systems not because they're actually useful for doing something, okay? So not because they model something that is seen in the real world necessarily, but instead creating number systems just because they obey algebraic properties. So creating number systems that obey nice algebraic properties rather than creating them because they mirror some structure in the real world, basically. Okay, and group theory is the foundations of abstract algebra. Okay, so the idea here is that we want to create number systems, basically. Groups are types of number systems, basically. Okay, and what fundamentally do we need to do in order to create a new number system? Well, what we need to start off with is just creating a bunch of symbols. So that's the starting point. But you know, just creating a bunch of symbols, does that really create you a number system? What else does a number system have? Okay, and to answer that question, let's have a look at a key example. Okay, so let's have a look at this number system of the integers, which I'll denote as z, like so. And I know that you can add and multiply integers, but for our purposes, let's do away with multiplication. Let's forget that multiplication exists, and let's just think about the integers with addition defined on them. Okay, so what is the integers fundamentally? It's a set, okay, so just use normal set notation here, and it contains loads of symbols. So you have 0, you have +1, you have -1, you have +2, you have -2, and it will go on and on. Okay, right, so there is our set of symbols, basically, okay. Now, that's not very interesting. If you just create a set of symbols, that's just a set of symbols. What's incredible about the integers is that it has addition on, okay? And as I say, we're forgetting that it has multiplication on, okay? In groups theory, we're only ever going to have a single composition law, and if you don't know what that is, I hope it will become apparent very soon. Okay, so we want to ask the question, what does addition really mean? What is addition? Okay, what does it mean to take one arbitrary element of the integers and add it to another arbitrary element of the integers? Okay, so x and y here are denoting arbitrary elements of this set, basically. They're variables. Okay, right. So basically, on this set, you have a way of combining any two elements together. You can put any one of these elements in position x here, and you can put any one of these elements in position y, and then you can combine those two elements, or those two symbols together to get another symbol within the set. That's what is incredible about the integers. That's what suddenly takes it from just being a set of symbols to being something interesting, to being a number system, basically. This way of combining two elements together, okay? And I'm going to introduce you to a bit of terminology now, okay? We will often, more generally, more abstractly, call this composition, Okay, so specifically here we would call this addition, but more generally we'll call it composition. Okay, and we'd say we're going to compose two elements together. Okay, so I'll just underline composition in red here. Okay, right. So that is what makes this set special. That's what makes it a number system rather than just a symbol, a set of symbols, basically, that you have this composition law defined on the set, basically, and we're going to use that to motivate how we're going to create groups and what a group is going to actually be. Okay, right, so let me now tell you about what a group actually is then. Okay, so a group, fundamentally, is just a set of symbols. Okay, so I'll denote my group as G here, okay, which is common notation. And then what you have to do is, if you want to create a group, if you want to create your new number system, which is going to be a group, okay, first and foremost, what you need to do is create some symbols, make up some symbols. Okay, so I won't make up my own symbols, I'll just use some arbitrary symbols. So maybe we could have capital phi here, maybe we could have lowercase phi, maybe we could have capital D. Okay, and I'll just have a really simple set of 3 elements here. Of course, the integers was a set of infinite size, basically, but you can make sets of finite size and make number systems where you only have a finite number of elements. And because it's easier for me to actually show a composition law for this, we'll do a finite set. Okay, so I've created a nice simple set of size 3 elements, basically. Okay, but that's not a group yet, that's just a set. That's the set that's going to underlie my group. Okay, but to turn this set of symbols into an actual group, what I need to do is define a composition law on this set of symbols, analogous to what I have in the case of the integers, where I can add any 2 elements together, or I can compose any 2 elements together to get another element. Okay, so basically, I need to be able to take any x, which is an element of my group, and compose it. And often the symbol that people use for composition is this more abstract circle, like so. X composed with y. Now I should just go over the symbols that people can use for composition. So there are loads of different symbols people use for composition. This is the most abstract one, putting a circle like so. Okay, sometimes you will see composition denoted by plus though. Okay, that's common in things like the integers. Okay, you can also see it as multiplication. Okay, multiplication is another way of composing 2 elements together. Okay, and we'll come on to that maybe a bit later. Okay, and also, if you want to compose 2 elements together, a common way of doing it is just to write the 2 elements next to each other. So xy means x composed with y. So these are all different ways of denoting 2 elements being composed together, basically. Okay, right. So I need to be able to put any element here in position x, and put any element from this group in position y, and I need to know what the answer is. I need to have defined what the answer is. Okay, so that really means that I need to have made you a composition table. Okay, so let me show you a composition table. Okay, so I'll put this circle here to show my composition. If I was calling the composition law addition, I would put add up there. Okay, and what I'm going to do is I'm going to put every element of my group up here. So here's capital phi, here's lowercase phi, here's capital D, and also along here. So I'm making a table, and then what I will simply do is I'll put in all the answers. So when I say little x composed with little y, okay, what that will mean is find little x in here from this side column here, basically. Take the row that corresponds to that little x, and then go along to find little y up here, and take the column that corresponds to that little y. So for instance, if I wanted big phi composed with big D here, okay, I would take big phi, capital Phi from here, and then I take capital D from here, so this would be over here, so this would be phi composed with D over here. Meanwhile, D composed with phi, the opposite way round, would be down here, D composed with phi. So be aware that that's how, not like that, D composed with phi. Be aware that that's how I'm going to arrange the orders, basically. So when you have them in the opposite order, this is how I'm taking the 2 elements, basically, from the composition table. Okay, right. So basically I need to go through and I need to put in what all the answers here are. I've got 9 entries that I need to fill in my composition table, and I need to define what every 2 elements composed with one another is. Now note, it is not necessarily the case, even in group algebras, and I haven't fully told you what group algebra is yet, that x composed with y needs to equal y composed with x. It's not necessarily true that the composition law needs to be symmetric down the diagonal line, so don't think that. So basically what I'm saying is that capital Phi composed with d, the answer up here, doesn't necessarily need to be the same as the answer here. Okay, right. So what you could do is you could fill in answers, basically. You could make up your own composition table. You could put in whatever answers you want here. However, if you just made it up, if you just put random answers in all of these 9 entries, okay, and of course you'd have to put answers from the original group. Okay, the answers do have to be one of these 3 symbols. You can't create a new symbol and put it in here. That's actually going to be one of my first axioms of group theory, which we'll come back to in a moment. Okay, so you need to put in answers into this composition table from your original group here, from your original set. Okay, but if you did that, if you just put in random answers into these 9 slots here, you probably will not end up with a group. Okay, you will end up with what you could call a number system, okay, because you've now got a set with a composition law defined on it, a way of combining any 2 elements together, but it's not going to be very interesting. It's most likely not going to obey any fancy algebraic properties. You're most likely not going to have any clever way of solving equations other than just trial and error. Okay, so it's probably not going to be a very interesting number system. Okay, and it's not going to be a group. So let me now tell you the properties that this composition law has to obey in order for it to be considered a group. And this is fundamentally what a group is. You create a set of symbols, you define a composition law on it, and this composition law has to obey a bunch of fancy properties that mean that you can actually solve equations in it, that there is some fancy algebraic properties to this, okay, in order for it to be considered a group algebraic number system structure. Okay, and this is exactly, I just want to stress this is exactly what the integers under addition is. Okay, the integers is just this great big set up here. Okay, and what we have done is defined a huge great composition table like this. Okay, so if I could just put this down here, the composition is called plus in this case. Okay, and what I could do is put in every element of the integers into my composition table here. So here's 0, here's plus 1, here's negative 1, here's plus 2, here's negative 2, and then I could go down here, 0, plus 1, negative 1, plus 2, negative 2, and I have just defined all the answers here. So 0 composed with 0, or 0 plus 0 is just 0, 0 plus 1 is plus 1, 0 plus negative 1 is of course negative 1, 0 plus 2 is plus 2, 0 plus negative 2 is, of course, negative 2. And you could go through and continue on filling in this table, and of course the table would go on and on and on. Now this composition, this addition composition on the integers, does of course obey the property that when you take one element x and add it to y, that's the same as if you do it the other way around, y plus x. So this one is symmetric down the diagonal line, but that is not actually a requirement for it to be considered a group, as we'll see later on. Okay, right. So that's my motivation for what we're about to do. The integers is just this set of symbols with this composition law defined on them. And as I say, forget that you've got multiplication defined on the integers as well. In group theory, we're only going to be defining one composition law. When you take sets of symbols and define 2 composition laws on it, that creates a more complicated algebraic structure. Okay, so we're not going to go there yet. We firstly just need to master group theory, where you create a set of symbols with one composition law on. So imagine that the integers don't have multiplication. Imagine it's just a set of symbols with this single composition law, which is addition defined on it. Okay, and that's actually going to obey all of the axioms of being a group, basically. Okay, so let's now go through the axioms of group theory. What properties does this composition law need to obey in order for this structure that I've created to be considered a group? Okay, right. Well, axiom number 1 is the simplest, okay, and you'll probably think this one's a bit trivial, okay, but it becomes important when we study subgroups, which we will do in a later video. Okay, so axiom number 1 is what's called closure. Okay, and basically this means that the entries in your composition table, okay, the 9 entries that I put here, 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 and here, they all need to be elements from my original group. I can't just suddenly create a new symbol, let's say zeta, and put it in as one of the answers here. That's no good at all. Okay, all of the elements have to compose together to give another element in your original group. Okay, and of course that's true in the integers. When you add any 2 integers together, you get another integer. So the integers under addition is closed. It does obey the closure property. Okay, so that's the first axiom that this composition table needs to obey, and that's a nice simple one. You can understand completely what that means. Okay, from the simplest one, we're now going to go to the most complicated one. Okay, the most subtle one to understand. Okay, and this is a really, really difficult one to actually get. Okay, so axiom number 2 then is associativity, and really associativity is what algebra is all about. And let me just make sure I spell it correctly. Associativity. Okay, so algebra really is just the study of associativity. Okay, this is the absolutely key property of groups, basically. Okay, and of most algebraic structures. Okay, so let me explain then what associativity means. So I have now told you this composition table. Let's say I've defined this composition table. Let's say it is closed. Okay, so every element that you get within this composition table, all 9 entries, are within my group. Okay, that tells me now how to compose any 2 elements together. So I know the answer to x composed with y for any x and y is an element of my group, basically. Okay, so I know how to compose any 2 elements together. What if I want to compose 3 elements together? X composed with y composed with z. Well, my composition law doesn't tell you how to compose 3 elements together. So what does this really mean? Okay, well, to make this mean something, what I need to reduce it into is composing 2 elements together. Okay, so what I need to do actually is put some brackets in here. So for instance, if I put brackets around x composed with y like that, what that now means, that actually means something now. Okay, because that means compose x with y, whatever x and y are, compose them together, which you can do because I've defined how to compose 2 elements together. Get the answer to that composition. Okay, so that's some answer now, and that's back in the group because we know it obeys closure. Okay, so this is another element now. Think of this as a single element. Then take that answer and compose it with this other element, z, which is again just a composition of 2 things. Okay, so by putting in those brackets, I've suddenly made this mean something, basically. Okay, because I've reduced it into the problem of composing 2 elements together at once, basically. Okay, so what associativity is all about is that it doesn't actually matter where you put the brackets. Okay, you see, I chose to put the brackets around x composed with y. Firstly, get the answer to x composed with y, and then take that answer and compose it with z. But what I'm saying is that I could do it another way. I could think of this as x composed with y composed with z with the brackets like so. Okay, so what I could do is I could firstly compose y and z together. Okay, so I could take y and compose it with z. Okay, that's a composition of 2 things, so I can certainly do that. That will give me some answer within the group. So now think of that as a single element. Okay, then take x and compose it with that answer. Okay, and again you will get an answer for what these 3 things composed together are. Associativity says that these 2 ways of doing this, these 2 ways of composing 3 things together, are the same. They will give the same answer, and I really want to implore you to understand how non-trivial that is. Okay, we think of that as being trivial because, of course, addition does obey that. Addition of integers does obey that. All of the other compositions that you probably have ever seen, like matrix multiplication, multiplication of integers, multiplication of real numbers, multiplication of complex numbers, whatever you like, they all obey that. Okay, so you think of that as trivial, but it is not trivial, not one bit trivial. If you just made up this composition table, if you just stuck in whatever elements you fancied in all of these 9 positions, I assure you that unless you knew what you were doing, you would not get it to obey associativity, basically. It's a good challenge. Try and build this so that it obeys that. You will have a real struggle, basically. It is not an easy property at all to actually build into your group here. Okay, unless you actually know what you're doing. Okay, so let me try and explain more why this is not trivial by showing you it's in the composition table. So let me just draw out my composition table here. Okay, so I've got 3 elements, so let's compose them together. So let me do phi composed with little phi composed with big D. Okay, so let's think about what we'd get if we did it this first way. Okay, so I'll just draw out the composition table again. So here is all of my elements down here, and here are, whoops, messed that up. Here's capital phi, here is lowercase phi, and here is D. Okay, so if I did it the first way, then what I firstly need to do is take capital phi composed with little phi. Okay, so I get this answer here, and then whatever that answer is, which I don't know what that answer is, I could define it to be whatever I want, okay, because I'm creating this composition table. You know, you could create that to be whatever you like, okay, but it will be one of these answers, and then you'll take whatever that answer is and then compose it with D to get one of the entries down here. Okay, so depending on what that answer is, the overall answer will be one of these entries down here, basically. And it will, as I say, depend on what this answer is. If it's capital Phi, then it will be this one here is the overall answer. If it's lowercase phi, then it will be this one here that's the answer. If it's if it's uppercase D, then it will be this one here that's the answer. Okay, now let me do it the other way around. Okay, so what I'm going to do is I'm going to take lowercase phi composed with capital D. Okay, that will be this element here, so I'll just write that in. So this is lowercase phi composed with capital D. So I'm now taking these two and getting their answer first, and then I'm going to take uppercase phi and compose it with whatever that answer is. So I don't know what that answer is because I haven't defined it yet. I could define it to be whatever I like, but then depending on what it will be, the answer now will be one of these entries here. So it'll be this one, or potentially this one. Okay, so in the first case, your answer is going to be one of these green ones down here. In the second case, it'll be one of these pink ones up here. Okay, I could define those to be completely different. So basically, this is not trivial at all. Okay, you end up with the answer being totally different entries in the composition table, so it's not trivial that this is true at all. Okay, this is the most difficult property of all the axioms that we're going to see, basically. Okay, and as I say, if you just make this table up, if you just put in entries, okay, if you just make it up, put whatever entries you like in all of those 9 slots, it will most likely not obey associativity unless you are very, very lucky, or unless you know what you're doing, it won't obey associativity most likely. Okay, right. So, what I now want to tell you about is I've shown you this very, very difficult property to actually understand and to get when you're actually building a group. Okay, but what I want to show you is how can you actually get this property then? How can you actually ever hope to build a group which does obey this property? Okay, and there is a nice way of doing it and a very nice way of thinking about it. So I want to show you that way of thinking about where associativity comes from and therefore how to actually build a composition law that obeys associativity, basically. But we'll do that in the next video.